once you design a digital circuit or a digital system, you want to implement it. And usually you implement it on a digital hardware. And there are several digital hardware options available, and they generally can be categorized under one of these categories. They're either standard chips, programmable logic devices, or custom design chips. So let's talk a little bit more about it. Standard chips. Probably you're familiar with these ones. Standard chips are just ICs that are readily available. You pick them off the shelf. They're super cheap, and they conform to very standard functionality. Once you buy them, that's it. They perform that particular function. For example, in here, I'm showing you an example of the chip, which is 7400, and it contains 4 NAND gates. And even if you need only one NAND gate, you can't do anything about the other NAND gates. They just exist because it's just a standard there. And of course, as you probably know, the 7400 series contains other chips that have NANDs, NORs, XORs, even BCD decoders. And if you want to build a larger system or something that does something useful, you probably would need a lot of these chips, kind of like what you see in here on the breadboard. So in this breadboard, I don't know what the functionality of the circuit, but what I wanted to show you is you really need a lot of these chips. Even if you're using some of them or part of them or whatnot, you need a lot of these chips, and this is not really neat. Neat is probably not scientific. What I mean by neat is they take a lot of space and they consume a lot of power. So in order for you, for example, to use this NAND gate, you need to power the whole chip. So you're even powering the other chips, even maybe you don't even need the other NAND gates, but you're powering the whole chip. So they consume a lot of power. So nowadays there are other options, the programmable logic devices and custom design logic. They're more efficient. They're actually the ones that are used nowadays. Nobody uses these. I think they stopped using them from the 80s. In the 80s, these custom standard chips were popular. You use them in an educational setting because they're easy to use and they're cheap and they're easy to understand as well to manipulate. So in this course, we're not going to be using that. We're going to be moving to something a little bit more modern. So we're going to be talking about programmable logic devices, or PLD, or in short PLDs. Okay, programmable logic devices that are different types of families of devices. They're all programmable logic devices. What they share in common is the following. When you bought the 7400, it was specific 4 NAND gates and that's it. So programmable logic devices are not like that. They're more of a blanket, some sort of a blank canvas for you, a blank digital canvas, let me call it this way, that you can program it to be whatever you want. So all of these families, regardless of which one you use, whether the PLA or the GAL or even the FPGAs, all of them are different technologies and you program them differently, but they all share the same feature that you can program them to be whatever you want them to be. Okay, whatever circuit you want them to be by internally programming certain switches internally. Okay, I'm not going to focus on the differences in terms of technologies between all of them. What we will be using are FPGAs because they're the most common and they're most recent nowadays. Okay, so FPGAs are field programmable logic, field programmable gate arrays. And in here, I'm showing you a couple of examples. This one here is an Altera chip, and Altera was acquired by Intel, so now they're Intel chips. And the other ones here are Xilinx chips, which were even recently acquired by AMDs as well. And of course, there are other manufacturers, but I'm just showing you the bigger manufacturers that take the most market share of FPGAs. So why FPGAs or why programmable logic devices? Well, they're very, very, very flexible. So flexible in terms of like, okay, you buy one chip, but you can make it to operate whatever you want. You want a bunch of NAND gates, a bunch of OR gates. Actually, it has thousands of gates in it. So you can actually do whatever you want with it. And they're also relatively cheap. They're probably not cheaper than standard chips, but they're cheaper than the other option we're about to talk about, which is custom design chips or custom design logic. So they're relatively cheap and they can be used to prototype a digital system from start to end very, very quickly. So you can actually design a circuit, implement it, play around with it, modify it, come back to it on the same exact chip, and it's not going to cost you much. Okay, and it's relatively also fast. Okay, so in this course, we will be using these FPGAs because of all these features, and they're very good for educational purposes because if you make mistakes, you can come back. Mistakes are cheap with FPGAs, at least in our settings. Okay, the last option of a digital hardware is actually a custom design chip. So a custom design chip, or sometimes I refer to it as custom logic, It's a chip that you actually design and you produce and you send it, and it will once it's produced, it performs the functionality you designed it to do, and you can't change it. So it's similar to the 7400. So it's similar to the 7400. However, it's not readily available. You design it, you send it to a foundry, and it gets fabricated. But the foundry is a very highly specialized manufacturing facility. So doing the custom logic is really extremely expensive. So it's expensive because it takes a lot of money to produce a chip. Okay, so because you need all the foundry, and this foundry actually is very expensive to build and maintain and so forth, and all the operators in it. But anyway, the techniques we will learn in this course actually will help you design these custom chips. Even though we're not going to be talking about custom logic, but whatever techniques we learn in here, you can actually utilize it and send it to foundries, or you do custom chips. So why don't we use custom chips? Well, again, they're very expensive, and the other thing is they take a significant amount of time. If you want to design some sort of a chip, whatever it is, a processor or any other digital circuit, it takes a significant amount of time to design, verify, to make sure that everything is okay before you send it, because mistakes are costly. Like if you send the chip and it turns out that there's an error in it, or there's some sort of a bug in it, it's very, very, very expensive. It could be in millions of dollars. So you can't do that like the FPGA. However, if you have the capacity or the capability to use it, you're going to see that the chip that you design is going to be very, very small, or could be very, very small, and also could be very, very low power. So compared to FPGAs or programmable logic devices, you'll gain that it has a lot more power efficiency, and it's probably much, much smaller. So FPGAs gives you flexibility, but it consumes a little bit more power and a little bit more space, while custom logic gives you less power and or consumes less power, potentially less power depending on the design, and also less space. But again, it's only economical if you're actually producing it on very large scale. So if you're Intel or AMD and you're producing processors that you're going to send to millions of people, yeah, it makes sense to actually go to a foundry and not use an FPGA, even though you can use an FPGA to design a processor and just ship it. But in that particular case, a custom logic is probably more economical. Okay. All right. So again, just to recap, so we have a bunch of digital hardware available to us. All of these hardware, regardless of which one we're implementing or which one we're using, at the very lower levels of abstraction, if you actually think about it, if of course it's electrons, they're usually transistors on a chip. And of course in a transistor, it's not only a transistor, you actually have a bunch of transistor circuits. And these transistor circuits, you combine them to actually get gates. We will not worry about this portion or this level of abstraction. We're going to abstract it all together. So whenever we design something on the FPGA, I just want you to know that eventually they're being implemented using transistors and transistor circuits and whatnot. But what we really have to think about when we design is actually just the logic gate level. So we're just going to put gates together, and that's how we're going to think about it. And the tool will help us to implement it in the transistors. So before I close this section, I just want to talk a little bit about FPGA development boards. So an FPGA is just a chip. So in here, I'm showing you a couple of development boards, and both of them have FPGA chips on them. So this one here shows me this particular chips. This is the Arctic 7 from Xilinx, and this one here is showing me the Cyclone V, which is from Intel or Altera. Okay. The dev board is useful in that you don't have to buy a chip and solder it or put it on a breadboard. Actually, you can't put it on breadboard. FPGAs are more complicated than normal chips, so you need certain powers to them. You need like very specific specification or technical specs to do that. So what we're going to be doing in this course is actually we're going to be using a dev board, an FPGA dev board. So the dev board has the FPGA and has a bunch of inputs and outputs and sensors. So the one we will be using is this one here from Xilinx, which is the Nexus A7100T, and it contains a bunch of switches, a bunch of LEDs in here, so you can actually turn them on and off. You even have an 7 segments in here. It has a couple of colored LEDs, some push buttons. You can also connect it to VGA from here, or even Ethernet, or even a USB from here. You can connect some analog inputs in here, and you can connect some external sensor in here. Not only that, it also have a microphone in here. It also has a temperature sensor in here, and somewhere below that board you will have like an accelerometer and gyroscope. There are other dev boards out there, but we have chosen this one. Of course, Intel produces different dev boards as well, but we're not going to be using them. And again, we're using an FPGA development board because it's just easier to develop. All you have to do is just code it and upload your code through USB and then test it on the board. And that's what we're going to be doing in this course.